So now we're going to talk about power ratings when we want to select a resistor. So after you've made your calculation, you look at your E24 series, you know exactly what sort of resistor that you need. The next important thing to consider is the power rating. So why? If we use a resistor that has too low a power rating for a high power application, what's going to happen is that there's going to be a failure of that component, that resistor. Yeah. So in many cases, in our coursework or whatever it is, it manifests by a burning smell. So every time you smell something burning, it could be a resistor that has failed. Okay, simply because the resistor is not able to handle the current or the power applied to it. So it's very important to calculate the power rating needed for that resistor. So these are three formulas to calculate the power needed for that particular problem. Okay, so P equals to IV, P equals to V square over R, P equals to I square R. So you can remember all these three formulas as is, or you can actually just remember one formula and derive this using P equals to IR plus V equals to, sorry, P equals to IV plus V equals to IR. Okay, so how I get this is that P, instead of using IR, I'm going to substitute the I by V over R. Okay, so I is V over R. And if I substitute the I with V over R, so V over R times V, so this will give me P equals to V times V is V square over R. Okay, and if I want to derive this, instead of substituting the I, this time I substitute the V. So V equals to IR. So P equals to IV. So I stays times V is now IR. So IR. So I times I is I square times R. And I've derived this formula. Okay. So depending on the situation, on the problem given, choose the correct formula. Okay. P equals to IV, P equals to V square over R, P equals to I square R. Very quickly, I is current, V is the potential, the voltage, R is the resistance. Okay. So as a general rule, choose a resistor with a rating that is twice as large as the actual power used. So carbon resistors come in different power ratings, 0.125, 0.25, 0.51, and 2. So you'll notice that they are multiples of 2. So for example, 0.125 times 2, you get 0.25. 0.25 times 2, you get 0.5. 0.5 times 2, you get 1. And 1 times 2, you get 2. So it's kind of easy to remember this, okay? So the greater the power rating of a carbon resistor, of course, the bigger it has to be in order to handle the higher current. So for example, work the example 3.8, I've got V equals to 6, I equals to 0.2. So I remember the three formula that I told you to remember. And since V is given, I is given, I use the formula P equals to IV. Calculated, and I realized that the power needed for this application is 1.2 watts, and therefore I choose one that is kind of almost double the power rating of 1.2. Closest I get is 2 watts. Okay, so I don't choose one, because if I choose a 1 watt power rating, it can't even handle the working power of 1.2 watts. So I need to choose double that, 2 watts. So let's look at some review questions. Question 1, given zero point 0.1 amps, 22 ohms. So they give the resistor and they give the current. So I think back about the three formula that I gave you. What formula P involves I and R? And I know that is I square R. Okay. So the current is 0.1 square. The resistor is 22. Let me press my calculator real quick. So 0.1 square times 22, and I end up with 0.22. So that is the power output here. Now, suggest a suitable power rating. Suitable power rating, remember, I'm looking at one that is double, at least double. So if this double, so times 2, will give me 0.44. The closest power rating is 0.5. Okay, if you look at this table over here, the closest is 0.5, this one. So therefore, power rating for this resistor I should choose is a 0.5 watt power rating. Okay, do the same for this one. And then if you got questions on this, let me know in class when you next see me. Okay, so how do we vary the current in a circuit? So the quickest and easiest way is, of course, to use a variable resistor. Uh, of course, what you can do is to, in our lab, like you pluck out one resistor from the breadboard, exchange it with another resistor, but that's going to be so painful every time you want to change the current, right? So in comes the variable resistor. We just need to take a screwdriver and rotate it clockwise or anti-clockwise to change the resistor, and therefore you change the current. Okay. So this is a variable resistor. When we tune the variable resistor, when we increase, let me write this down. When we increase the resistance, the current decreases. And when the current decreases, the bulb becomes dimmer. When we decrease the resistance, the current increases. And when the current increases, the bulb gets brighter. Okay, so remember this relationship over here between resistance and current. So how do we connect a variable resistor? So a variable resistor, a trim pot, like I was telling you just now, has 3 legs. This diagram shows you what's going on in the 3 legs. Okay, so first off, rule 1 is always connect the middle leg. W stands for wiper. Why is it wiper? Because this fella, which is connected to the W, what it does is that it is able to rotate clockwise or anti-clockwise. Okay, so when you take a screwdriver and you rotate this Phillips head slot here, you're actually turning this wiper clockwise or anti-clockwise. Okay, so always remember, you must connect the wiper. Always connect the wiper. Next, you can either choose to connect A or B. So let's say I connect A. Let's say I connect A and I connect the wiper. Okay, and this is what it looks like. The current comes here, goes through the resistive strip, meets the wiper, goes up the wiper, goes up, and through to the rest of the circuit. Now, if you put your wiper, at this position, at the pink position, that means the current, let's choose this purple, that means the current would have to go a longer way round the resistive strip, meet the new position of the wiper, and go through here. This pink color line that I've drawn, because the current has to go through a greater amount of resistive strip, means that with this wiper position over here, you have increased the resistance. Okay, so that's how it works, like so. So that's how a trim pot works. Okay. Now, it is a good habit, though. It is a good habit to short the wiper and position B. Even though you may not be using position B, but it's a good habit to short it. So why? Because there might be a situation. There might be a situation if, let's say, you're being very rough with the trim pot and the wiper breaks. So, for example, if the wiper breaks, okay, let's say there's a break in the wiper over here. The current comes over here, over here, over here, over here. It sees that, oh, there is a break here, there's an open circuit here, no point going. So it'll come, but there is nothing over here to continue with the circuit. So in this case, what you have here overall is an open circuit. An open circuit means that current doesn't flow, light is not shining from the bulb, and it's going to be so hard to troubleshoot because you can't see the break in the wiper. So you don't know, hey, why is nothing being lit up? Because you can't see the break in the wiper means you can't really tell what's going on. And it's going to be such a headache to troubleshoot. But if we short this, if we short wiper and B, okay, now what happens? So let's choose a yellow. So current comes, current comes, current comes, current comes, current comes, passes through, passes through, passes through, finds that, oops, there is a break here, there's a hole here, there's an open circuit here, no point going. So what it does is that it comes, it comes, it comes, it comes, it comes over here, goes up. Because now we have shorted the wiper and terminal B, it is able to come here and complete the circuit, and light still comes out of the bulb. Now, in this situation, you can't really vary the resistance simply because you have made a direct connection between A and B. You have now taken the full resistance of the variable resistor. So if this were a 1 kilo ohm resistor, you are left with a fixed resistor of 1 kilo ohms. Okay? Uh, Hey, but at least you know that uh, by tuning it, if you're not getting a variance in the light, means there is something wrong with the variable resistor itself. So it is giving you a clue to where potentially there might be a problem to troubleshoot. Okay, so it's a good habit. It's not a must, but it is a good habit to short the wiper and the unused terminal. Okay. Another good habit is, of course, to use a fixed resistor with the variable resistor. Why? If I only have a variable resistor, a trim pot here, if by accident you rotate it in a wrong direction, and what you've done is that you have rotated the wiper over here. What you have done actually is that you have reduced this to 0 ohms, because the current comes here, current comes, current comes, current comes, goes through here, meets the wiper, goes directly up and through. It does not go through any bit of the resistive strip. And if it doesn't go through any bit of the resistive strip, you are basically giving it 0 ohms. 0 ohms, you're effectively shorting this whole trim pot out. And this is very dangerous because a zero resistance means that there's going to be a super high current. A super high current means potentially you might be damaging your components. So to prevent this super high current from happening, I'm going to always put a fixed resistor in series with a variable resistor, so that in a case whereby by accident you put this to be 0 ohms, at least I've got some fixed resistor in order to limit the current somewhat, so that I don't have a surge or spike in current to damage the component that I've connected this to. Okay, so uh, if I need a 270.2 ohm based on my calculation, what I'm going to do is that I'm going to put 240 ohms in series with a 0 to 100 ohm trim pot. So I've got a one fixed resistor of 240 ohms in connection to a variable resistor of 100 ohms, so that I can tune this fella. I can tune it to give me a close enough resistance of 270.2 ohms. Okay, I don't put 500 ohm trim port and then try to adjust it nicely to 270, because I want a fixed resistor in series with the variable resistor. Okay, so if you look at this review question, I'm going to do a drawing for you. So always remember, I want to connect my wiper, the middle one. Okay, so figure one, draw the connection. So first of all, make sure that I draw the wiper. Okay, can, and this is going to go to the bulb, and then from the bulb, it is going to go back to this. So I've completed the circuit like so. But remember what I told you, it is always a good habit. So let me draw for you the flow of the current, right? So the current flows here through the variable resistor, flows here through the bulb, lights up the bulb, and then back to complete the circuit. But I told you it's also a good habit to short the wiper and the unused leg, so that if there's a break in the variable resistor inside the component, uh, the bulb will still light up. Okay, can. So this one, clue, always use a fixed resistor in series with the variable resistor. Okay, but always remember to check the E24 series to find out the exact value of the fixed resistor you want to use. Okay, so that's it for resistor. Um, Review any part of the video, whether it's part 1, 2, or 3. If you're not sure, do chapter 3 worksheet provided for you. And if you've got any more questions, please look for me in class, or you can email me your questions. Okay.